traveling to the center of the Earth, whether through walking or advanced technology such as an underground shuttle, is purely theoretical at this stage, as no human has ever been able to penetrate deep into the Earth's crust, let alone reach its core. However, if we were to explore this concept further, we can analyze potential issues in terms of geology, environmental concerns, and hypothetical scenarios. 1. Scientific and physical challenges. Temperature and pressure. The Earth's core has extreme temperatures, up to 5,700 degrees Celsius, and pressures, over 3.6 million atmospheres. Even with advanced technology, creating materials and systems that can withstand these conditions is currently beyond human capability. Any breach in containment could lead to catastrophic failure. No known material can withstand these conditions for prolonged periods, making it impossible to construct a vehicle or tunnel that could survive the journey. Geological instability. Drilling or tunneling to the center of the Earth could destabilize the planet's crust, potentially triggering earthquakes, volcanic eruptions, or other tectonic activity. Magnetic field disruption. The Earth's magnetic field is generated by the motion of molten iron in the outer core. Interfering with this process could weaken or disrupt the magnetic field, exposing the planet to harmful solar radiation. 2. Environmental and ecological impacts. Release of harmful substances. The Earth's interior contains toxic gases, heavy metals, and radioactive materials. Disturbing these could lead to contamination of the surface environment, affecting ecosystems and human health. Climate effects. The release of heat and gases from the Earth's interior could alter atmospheric composition and contribute to global warming or other climate changes. Disruption of geological cycles. Human interference with the Earth's core could disrupt natural processes like mantle convection, which plays a role in plate tectonics and volcanic activity. Extreme temperature gradient. The Earth's temperature increases with depth, a phenomenon known as the geothermal gradient. On average, the temperature rises by about 25 to 30 degrees Celsius per kilometer in the crust. By the time you reach the mantle, temperatures range from 500 degrees Celsius to 900 degrees Celsius, and in the outer core, they soar to 4,000 to 5,700 degrees Celsius. Immense pressure gradient. Pressure also increases with depth due to the weight of overlying rock. At the Moho discontinuity, the boundary between the crust and mantle, pressure is already around 10,000 atmospheres. By the time you reach the inner core, pressure exceeds 3.6 million atmospheres. Structural integrity. The pressure would crush any known structure or vehicle. Even diamond, the hardest natural material, would deform under such conditions. Maintaining a pressurized environment for humans would require technology far beyond current capabilities. Climate effects. Greenhouse gas emissions. The release of methane and carbon dioxide from the Earth's interior could exacerbate global warming. Methane is a potent greenhouse gas with a warming potential many times greater than CO2. Heat release. The immense heat from the Earth's interior, if transported to the surface, could contribute to localized or even global temperature increases, altering weather patterns and ecosystems. Aerosol emissions. Volcanic ash and particulate matter released during the process could block sunlight, potentially leading to cooling effects in the short term but disrupting ecosystems and agriculture. Formation of new geological features. Changes to mantle convection could lead to the formation of new mountains, rifts, or other geological features, altering landscapes and habitats. 3. Logistical and technological issues. Energy requirements. The energy needed to drill or tunnel to the center of the Earth would be immense, potentially requiring unsustainable resources. Waste management. Excavating and transporting materials from the Earth's interior would generate massive amounts of waste, which would need to be managed to avoid environmental harm. Safety risks. The journey would be fraught with dangers, including equipment failure, structural collapse, and exposure to extreme conditions. Heavy metals like mercury and lead could poison ecosystems and accumulate in the food chain. Radioactive materials could increase background radiation levels, posing risks to human health and wildlife. Acid drainage. The interaction of water with exposed minerals could produce acidic runoff, harming aquatic ecosystems and contaminating drinking water supplies. Energy requirements. Drilling and tunneling. Drilling through the Earth's crust alone would require an enormous amount of energy. The Kola super-deep borehole, the deepest human-made hole, reached just 12.2 kilometers and took decades to complete. Reaching the center of the Earth, approximately 6,371 kilometers, would require exponentially more energy. Heat and friction. The friction generated by drilling or tunneling would produce immense heat, further complicating the process and requiring advanced cooling systems. Power source. The energy needed for such an endeavor would come from non-renewable sources like fossil fuels, raising concerns about carbon emissions, resource depletion, and sustainability. Ecological damage. Habitat destruction. The construction of tunnels, drilling sites, or infrastructure could lead to the destruction of habitats on the surface, displacing or eliminating plant and animal species. Pollution. Contaminants released during the process could pollute soil, water, and air, harming wildlife and disrupting food chains. Invasive species. The creation of new pathways through the Earth's crust could allow invasive species to migrate, potentially upsetting ecological balances. Navigation and communication. Magnetic interference. The Earth's magnetic field and the conductive properties of the mantle and core would interfere with navigation and communication systems, making it difficult to maintain contact with the surface or determine location. Unknown terrain. The Earth's interior is poorly understood, and unexpected geological features could pose additional challenges. Mapping the interior in real time would require advanced sensing technologies. Autonomous systems. Given the extreme conditions, much of the operation would need to be automated, requiring reliable and sophisticated artificial intelligence and robotics. Human survival. Life support systems. Providing oxygen, food, and water for an extended journey to the center of the Earth would be extremely challenging, especially in such extreme conditions. Life support systems would need to be self-sustaining and highly resilient. Psychological stress. The isolation, darkness, and constant danger would take a significant psychological toll on explorers. Maintaining mental health and morale would be a critical challenge. Physical health. Prolonged exposure to extreme conditions, even within a controlled environment, could have serious health consequences, including physiological stress, radiation exposure, and long-term effects on the body. Return journey. Gravity and buoyancy. Returning to the surface would require overcoming the Earth's gravitational pull and the buoyancy forces of the dense mantle and core materials. Structural integrity. The vehicle or tunnel would need to withstand the same extreme conditions on the return journey, increasing the risk of failure. Energy requirements. The energy needed to return to the surface would be considerable, adding another layer of complexity to the endeavor. Material degradation. Even advanced alloys, ceramics, and composites would degrade or melt under such conditions. Developing materials that can endure these extremes is currently beyond human capability. Redundancy and fail-safes would be essential but difficult to implement. Structural collapse. The immense pressure and geological instability could lead to tunnel or vehicle collapse, trapping explorers or releasing hazardous materials. Emergency response. In the event of an emergency, rescue operations would be impossible due to the depth and extreme conditions. Explorers would need to rely entirely on self-rescue capabilities. 4. Long-term planetary consequences. Structural integrity of the Earth. Removing material from the Earth's core or mantle could alter the planet's mass distribution, potentially affecting its rotation, gravitational field, and orbit. Unintended consequences. The Earth's interior is not fully understood. Interfering with it could have unforeseen effects on geological and biological systems. Ethical considerations. Such an endeavor would raise questions about humanity's right to alter the planet on such a fundamental level, especially if it risks long-term harm. Climate instability. The cumulative effects of greenhouse gas emissions, heat release, and changes in geological activity could lead to long-term climate instability, making the planet less habitable. Geological instability. Crust and mantle dynamics. The Earth's crust and mantle are in constant motion due to plate tectonics. Drilling or tunneling through these layers could destabilize the surrounding rock, leading to earthquakes, landslides, or volcanic eruptions. Magma chambers. Tunneling could intersect magma chambers, releasing molten rock and gases to the surface. This could cause catastrophic volcanic activity and environmental damage. Changes in rotation could alter the length of days and nights, affecting ecosystems and weather patterns. Perturbations in Earth's orbit could lead to climate instability, with potential effects on glaciation, sea levels, and overall habitability. Consequences of disruption. A weakened magnetic field would reduce protection from solar radiation and cosmic rays, increasing the risk of cancer, damaging ecosystems, and potentially harming technology like satellites and power grids. Biological consequences. A weakened magnetic field could increase mutation rates in organisms, harm migratory species that rely on the magnetic field for navigation, and potentially disrupt ecosystems. Magnetic field generation. The Earth's magnetic field is generated by the dynamo effect, which is driven by the motion of molten iron in the outer core. Interfering with the core's structure or flow could weaken or destabilize this process. Release of harmful substances, toxic gases. The Earth's interior contains gases like hydrogen sulfide, H2S, methane, CH4, and carbon dioxide, CO2. These gases could be released into the atmosphere during drilling or tunneling, posing a risk to human health and ecosystems. Heavy metals and radioactive materials. The mantle and core contain concentrations of heavy metals, e.g., uranium, thorium, and mercury, and radioactive elements. Disturbing these materials could lead to contamination of soil, water, and air, causing long-term health and environmental problems. Acid drainage. The interaction of water with exposed minerals could produce acidic runoff, harming aquatic ecosystems and contaminating drinking water supplies. Excavation waste. Drilling or tunneling would generate massive amounts of rock and mineral waste, which would need to be stored or disposed of without harming the environment. Energy waste. The process would require vast amounts of energy, much of which would be lost as heat, reducing overall efficiency and increasing environmental impact. Density and composition. Density variations. The Earth's interior is composed of layers with vastly different densities. The crust is light, while the mantle and core are much denser. Navigating through these layers would require overcoming significant gravitational and buoyancy forces. Chemical composition. The core is primarily composed of iron and nickel, while the mantle contains silicate minerals. These materials are chemically reactive and could corrode or damage equipment. Hydrological cycle. Changes in geological activity could affect the Earth's water cycle, altering precipitation patterns, river flows, and groundwater levels. 5. Potential for minimal repercussions. If humans could develop technology to travel to the center of the Earth and return without disturbing its structure or processes, the repercussions might be minimal. However, this would require non-invasive technology, methods that do not involve drilling, tunneling, or removing material from the Earth's interior. Energy efficiency. Systems that do not rely on unsustainable energy sources or generate excessive waste. Environmental safeguards. Measures to prevent contamination or disruption of the Earth's systems. Ethical and societal concerns. Environmental justice. Communities near drilling or tunneling sites could endure the most of environmental damage, raising issues of equity and justice. Intergenerational impacts. The long-term consequences of such an endeavor could affect future generations, who would have to deal with the environmental and ecological fallout. Cost and feasibility. Economic cost. The financial cost of such a project would be astronomical, exceeding the budgets of even the wealthiest nations or organizations. The return on investment would be unclear, as the scientific benefits may not justify the expense. Time frame. The project would take centuries to complete, requiring long-term commitment and stability from governments, organizations, and societies. Conclusion. Is truly minimal impact possible? While no human technology today makes this feasible, theoretically, a civilization with the following capabilities could attempt it with negligible repercussions. 1. Matter phase shifting, no drilling needed. 2. Self-contained, zero-waste energy, and life support. 3. Ultra-stable force field shielding. 4. No mass removal or waste left behind. 5. Instantaneous exit protocol until such advancements exist. However, the risks remain too extreme to justify any attempt. But in the far future, with sufficient mastery of physics, the dream might someday be realized, without harming the planet. Thanks for watching this video. If you enjoyed it, please be sure to hit that subscribe button to our channel and hit the bell for the next video to release so you can get a reminder. And if you feel even more generous, be sure to give it a share, a thumbs up, and a comment. We look forward to seeing you on the next one.